Uh, Good. Okay, so I think make sure that everything is on. Recording is going there. Okay, so today we are continuing again the story I will mention about the class. We talk about some coverage problem, then we talk embedding into trees. Trees are the easiest problems to solve. Like easiest set of network that we can solve lots of problem in polynomial time, and we are continuing that. We talk about connectivity problems, then we say that okay, this not only you can do the regular problem Steiner tree, Steiner forest, but you can go byte network design, very real world practical problems, and we can solve them, and then all of them somehow embedding into tree helps one way or the other. Sometimes it would be the whole solution, like for the uniform case, uniform bias bug, but sometimes it will be part of the solution, like a non-uniform bias bug, but it helps. Now, I mentioned that before that these are for the cut problems that you want to connect the connectivity problem that you want to connect the people or send the flow. There are cut problems that you want to cut it, essentially, say for security or other things. And of course, there are some assignment problems or that, like, for example, matching or facility location and others that we will talk more later. But one thing that is still remaining is the part about cut problems that we want to talk about. Having said that, actually this result for the cut problem, they came out of this work of Oblivious routing. This is the one that actually the credit goes to Harold Räcke for this part. So this is for Oblivious routing. And this is the one that goes to Harold Räcke. So I already mentioned some of this previous time when we talk about the universal solution, Oblivious solution. I want to just have a recap on that, finish that. And then all of this works also came from this Oblivious routing. So this Oblivious routing is very important for two things. One, for the Oblivious universal, incremental algorithms. And the second one is because of the essentially for tree embedding for cut problems. So that's the thing that we are talking about. And both of them are very important, and we will talk about it. And both of them, again, these are some kind of frameworks. We are talking more about framework. The first one, you can now think about this way of thinking about problem, as I mentioned. If you can get any such solution, it is really appreciated because the people love this kind of very general solutions that independent of your input, you give a solution which is good. And the other one, of course, again, this is some kind of tree embedding for cut problem that you can solve lots of cut problems there. And we will talk about both of them essentially in this session and probably the next session as well. Good. Now, before going through this, so these are the two important things. I wanted to go and recap essentially the thing that we have mentioned for this. Good. So previous time, we mentioned this is oblivious routing that I will define, but I mentioned that this universal solution, they have been there before. And in particular, some of this uniform solution that this was, one of them was essentially about this universal TSP, that here you want to find a total ordering. So the idea is that I'm giving essentially a tool for you, a guide for you, that you can use it independent of, the demands that you have it. So what is the problem? In the TSP, you are a set of points that are given, like in the plane, for example, or in the planar graph, it's a subset of them. And you want to go and visit them, and you want to visit all of them and come back to the same place. So Here, in general, given a metric space, you want to get a total ordering of points of the space such that for any finite subset, this is the input essentially, or the demand set, the tour which visits these points in the given order is as close as possible to the optimal tour. And this is called the universal TSP. So you want to find this solution such as it is like this. And as I mentioned, the universal solution are motivated. Somehow there more work is done for universal solutions. We have done some of this work that I will talk about it after this oblivious routing algorithm by Harold Räcke. However, the early versions were there before. In particular, universal TSP first considered by Platzman and Bartholdi in JCM. JCM is like a top journal essentially in computer science in '89. And so this was the case that it was considered for the plane case. And you can, essentially this was the whole concept of a space filling curve. Because if you consider in the plane, what's the solution for the plane? So there are infinite number of points essentially here. So you need to find some kind of a space filling curve that goes to every point. And it should go, of course, that's the thing that is called a space filling curve, because it needs to go on so you need to describe what will happen in any sub areas, because again, it's still infinite number of points essentially are there. But a more cleaner problem is the case for planar graphs. So you can consider essentially this is a planar graph that you can, again, draw it on the plane without things. And each of them, they have a weighted, essentially, you can consider essentially the metric compilation of that or of this graph. And then say, is this planar graph, can you give me essentially whether for planar graphs, can you give an ordering of the vertices that you will start from here? So you can start from any place essentially, and you will go there. And that was the idea. You will give the ordering. If there is a demand there, you will go there. If not, you will just bypass that and you will go to the next one via the shortest path. This is the thing that we had it. We had the first result on that. I believe actually even the upper bound for this was log n in this paper. You can just take a look at it. This is the Hajiaghayi Kleinberg-Layton in 2006. We give the first lower bound for the both plane graph and planar graphs. This is a complicated one actually, and it was, I believe it is slightly improved by Kleinberg and another quarter more recently. But the main thing is that you could actually get something like log to the 1/6 essentially. You could improve this 1/6 to something a bit better, closer to log. I think the conjecture is that the correct answer for this should be log n over log n, but we are not there essentially. So we obtained the first one. This is log to the 1/6, was for both plane graph. Plane graph means something like this, which is two-dimensional case, and planar graph means something like this. So this is plane, and this is planar. So this was obtained essentially, and I think even for planar graph, we had it log n or log n to the 2 as the upper bound as well. And here, when we talk about this, we talk about the competitive ratio. Competitive ratio is that, like, you want to say among all the demands that you have, all possible demands. So here, for example, if there are n vertices, 2 to the n is the number of set of demands that you can have. Over all 2 to the n, you will take the worst case of your solution versus the optimum solution. And that will be the competitive ratio for this Oblivious. And there you can show actually is the log n is the lower bound. So log n is the upper bound for planar graph, I believe. I think log n or log n, but I believe most probably log n. It is in this paper. You can check that. For TSP means subset of it. A plane graph means essentially this is two-dimensional, I mean, R2 essentially, just plane. You will draw this graph, and the points are essentially have X, Y. In the planar graph, there is no X, Y, but I mean, essentially you can do it on plane, or you can say more generally on a sphere. You can also draw it, I mean, as a plane graph. There are some close relation, but they are not completely the same. Generally, planar graphs are harder than plane graphs. That's a typical idea. Good. So this is the thing that is there, and this was a square root of log n. That is for plane, both for plane and planar graphs, and for we could actually show log n for and n is the number of points essentially for planar graphs as well. There was no such bound before this paper that we mentioned it. But for general graphs, there is a lower bound of log n for expander graphs. So for expanded graphs, you say that for TSP, you cannot get better than log n in general graphs. However, I think this is the result there. But the upper bound, the best upper bound that exists for general graphs, is again our result by Anupam Gupta, me, and Harold Räcke, that we show actually log n to the 2. So there's a very interesting gap between this lower bound of log n and log n to the 2 for this universal TSP. So that's the current thing, essentially the state of the art. We know that for expander is log n, but I mean, the belief is that log n probably is the correct answer, but we don't know the things as of now. Good. This is the other things that I have mentioned previous time. So in the Oblivious by-at-back network design, so this result that we have log n to the 2 for TSP actually is coming out of general things that for network design. This is the paper again that we have it with Anupam Gupta and Harold Räcke in 2006. So this is a very general result that I mentioned briefly previous time. So in the general multi-commodity flow that we talk about, uniform or non-uniform by-at-back, there is a non-decreasing monotone submodular function, subadditive function. So this is f, that for each edge E, so that if FB is the minimum cost of the cable installation with bandwidth B for this. So essentially we have this f of B, and this f of B is monotone subadditive function in general. And subadditive means that if there are essentially C of X plus C of Y is greater than or equal to C of X plus Y. It would be uniform if this f of E is the same for all edges, and it would be non-uniform otherwise. So as we mentioned, there is a log n algorithm for non-uniform case by Bartal that we talk. Log n to the 4 essentially for general non-uniform that we discussed previous time. This is the result that we had it, and there was some improvement for if the demands are polynomial instead of exponential. But the interesting thing is that the Oblivious version is, this is the one that you decide. So what is the problem? That is the interesting part. And again, I will say these are amazing things, and because it's quite non-trivial that there exists such a solution. That this by-at-back is given in the uniform care version. You can actually, when this f of E is given to you, you can decide about the path in advance in this graph. So you will say if these pairs, and there are n choose 2 pairs that are coming essentially, and the demand is just the demand di. Because as I mentioned here, we can always say that we are sending through one path essentially. So these demands are coming for me. So the demands are coming essentially on a different part. For each demand, I will give you a path in advance. So this n choose 2 demands. all of them are coming. I mean, they are essentially, I give you the path in advance. Now, whenever some of these demands are coming, just use my path. This is for buy at buck. So this is like the thing that you are just using my path. You know, it is, again, theoretically, these are very appealing, and this is like some kind of ultimate result, I will say. Why? Because this is that I don't. You just give me all this sharing, etc. I don't care. Just use my path. My path is comparable with the best thing that you can work essentially, and even exponential time you spend it to find the best solution for your instance. My solution in this case, at most, order log n to the two worse than your solution. It is like theoretically it's very appealing and again very non-trivial because it is one level higher than approximation algorithm. In approximation algorithm, we only care about just for this instance, can I compare to the optimum? Here say no, forget about this instance. Any instance you will give it. I will give a solution in advance to you. Just use my solution, my prescribed solution. It is comparable for your optimum on that case. And this optimum can change quite a bit. That's the thing that is called essentially universal solution. So this log n to the two that we mentioned, it was not improved. This is, I think it becomes much even more important results because I mean there's no improvement actually has been done as far as I know to this. So still between log n to the 2 and log n, this is an open problem. And this is the same thing. Generally, also this is the case. When you get it for a Steiner tree, a Steiner forest, then you can get for TSP. TSP is coming quite easily with this one. And what is the idea? Because TSP essentially is like we have it done for price collecting problems for Steiner tree, and then it works for TSP. Generally, TSP and MST are not that much far from each other because if you want to find, essentially, if you want to visit these points I have mentioned briefly. So generally, the way to find the tour is that you are finding first an MST because any tour anyhow needs to connect these guys. So MST is a lower bound for that. The only issue that, I mean, this MST, you may want to make it Eulerian. So then if you want to do essentially from, I mean, one way essentially is that you want to make essentially this MST as a Eulerian thing, then you can go actually through all of these points. You see that you can go there. The only thing is that to get a better approximation than this, you may, what you do essentially, you, instead of doing this part, what do? You are doing something, if you will find a matching between essentially odd degree vertices here, then you can say that the cost of this matching is at most half of the optimum solution because if you have the optimum, you can create this matching one way or the other between these odd degree vertices. So this matching, okay. So you have this matching, which is the half opt, and this MST that it is essentially opt, and this is like half of plus opt, then you can get 3/2 approximation for TSP. And then this was this recent improvement that you can actually get nowadays something 3/2 minus epsilon for some constant epsilon. Now you can get a little bit better. Anyhow, so that is for the TSP, and these problems is like MST and TSP are very, like TSP and MST are very similar to each other. So that's about this one and the TSP. I wanted to say that this is a very important one. TSP, why? Because the original, so in some sense, the universal solution first was considered for TSP, and that was the important thing. Now, let me clear this one. Now the next one, this is another one that actually, this is also interesting, and this is another. So far we talk about oblivious network design. Means that you are essentially oblivious network design, you decide about the path in advance before the demand. Then we had this universal thing that essentially an ordering is given to you, and whenever some people are not there, you can just remove some of these things. There is another thing along this one. It is called incremental solutions. This is also come out of the same generalization, essentially, almost the same time as well. What's that? Yeah, yeah. That means I mean Averbach, I think, and Bartal, because I think Bartal improved it to Lagen or something like. Yeah, because I think, yeah, you should see the original paper. I think, as I mentioned, they were using Bartal, but essentially using Bartal technique here. I mean, so here by Bartal technique. Uh, this incremental solution is another one which is actually very interesting. And again, you can think about this one in your own research as well. Good. Okay, so the next thing that we are talking about is in our incremental solution. What are the incremental solutions? So this somehow in between these two problems, universal solutions and this universal solution, oblivious solutions and universal solution. So here, what is the incremental solution? And the incremental solution is you want to order the solutions of for different cardinality k for a parameter k that we will talk about it, such that for all values of k, the solution respects the ordering. And for any k, the solution is the close in value to the value of an optimum solution for that cardinality k. So let's see some examples. What is the k-median problem? We will talk more about it. So k-median is that you are given a graph, is a metric. You want to open case essentially k places here. Select k places here, such that everyone goes to the closest person, and some of the distances are minimized. So again, you want to open k. These are k centers. K center. Actually, there's a k center problem as well. So in the k median is the one that you want to open k problems, k centers. Everyone goes to essentially everyone in the graph goes to one of these that is closest to that, and then some of these distances will be minimized. That's the problem for k median. K center, the same problem. Instead of sum, we talk about the max distance that should be minimized. Good. Now, what is incremental solution is this? Here, the important thing, of course, is k. And it is important for k median, the solution k versus k plus 1 can be very different. Just think about this example. So for example, if this is the whole graph that you have it. This is a very long path. Good. Like, essentially, you can just think about it like these things. So this is like, I don't know, 100 here, 100 here. Good. And you can actually see that maybe actually this is another one here as well. So the length between these guys is 1000 as well. So, and these are like so you have 4 vertices. These. But no, in this case, if you have k is equal to 1, then I mean the solution can be one of these people essentially. Either this vertex or this vertex for the k median, correct?
So are you so is your output like a big
No, I mean, for now, just forget about this one. I'm talking about just k median. K median problem, if you have k is equal to 1, in this case, you want to find one center such that, I mean, you will minimize the total cost to the center.
My point is that, like, I don't know, like, let's say you're putting k median, you're not constrained to have your output, you want to the
Yeah, I mean, the graph case, I mean, yes, I mean, generally, you are not, I mean, you can be any vertex, the Euclidean case essentially, or the plane case. But you can say that one of the centers, one of the vertices. If one of these vertices, then you can do this one, and then I think in both cases you need to pay this 1,000. However, if k becomes equal to 2, then you are just essentially opening one of these centers, say this one and this one. None of these two guys. And then you don't pay this 1,000 anymore. Good. So the solution for k and k plus 1 can be completely different. However, what is this kind of k incremental solution? Here, for k median, you want to give the so for k median, you want to give essentially the centers. So this is the C1, C2, Cn. Let me say you can have n vertices in the graph. N is the number of vertices in the graph, or in the metric essentially. So I want to give an ordering C1 to Cn such that whenever you want to, for any k, you just get the first k. So I want to give essentially for k median, give you as output an ordering such that if you want to get k equal to 1, just take the first. K equal to 2, the first two. K equal to any k, just take the first. So I respect the previous solutions. And this is important again, why these incrementals are good, because say you want to create essentially like you want to have a city. Maybe in city currently 1 center is enough, or 2 centers are enough. But later you may want to add more centers to that. So it is the case that whenever the population becomes more, or like there are more things is needed, then you can just add one more and you will keep the previous one. You don't need to completely create a new places center such that you can get the previous one. Just respecting the previous one and adding this one. This is essentially has been used for this one, or another problem called K-MST. What is the K-MST? The K-MST is that essentially in the MST, you want to find minimum, so you are given a graph, and you want to, in the MST, you want to connect all of these vertices. In the K-MST, you want to connect essentially, you want to have essentially a tree on k vertices. And of course, if k is equal to n, K-MST and MST becomes the same. Good. Now, what is the things that you want to do it for K-MST? So for K-MST, the main goal is to create essentially this like for K-MST, the main goal is to essentially select. If you have k edges, you can see that you have, or k minus 1 edges, you can have k vertices. So in the K-MST, it is like that. And the k is given to you. So you want to say that for any k, I want to connect only k guys. Then in this case, I want to give an ordering on the edges such that if for any k between 2 to n, the first k minus 1 edges of the sequence span k vertices that you want. So K-MST, you want to connect k vertices. So I'm giving you the ordering of edges. And I say that if you want to find 2 MST, take the first, essentially the first edge. If you want to get 3 MST, then get the first 2 edges, and so on and so forth.
The K-MST, like your input is like endpoints. And let's say case 3, you just want to connect any 3 points.
Any 3 points. You can have the rooted version that you want to connect to the root or not. And there is this generalization, it is called K-Steiner tree. What is K-Steiner tree? You are given some terminals and you want to connect some of these K versions. K of this. Interestingly, there was a gap too between this K-Steiner tree and K-MST. But we showed essentially the paper by Bateni and Hajiaghayi. We showed that actually K-MST and K-Steiner tree, these are the same problem. So there's a reduction. So K-Steiner tree is not harder than K-MST. And for all of them, the best approximation is 2 approximation for this K-MST or K-Steiner tree, or all of them is the 2 approximation. And this was also, it was the long things essentially that the people have there, from SVR root of n to log n to constant. And then it was so interesting that there was some constant factor before, and then there was a stock paper. So there was 2 plus epsilon approximation before, and there was a stock paper, I think, by Navin Garg, who showed that actually says saving epsilon. So there was a stock paper to just remove this epsilon and make it 2. Big open problem, getting something better than 2 for K-MST. For K-MST, or as I mentioned, K-MST is the same, getting better than 2. So better than 2, approximation factor 2 for K-MST. That's a very big one. But anyhow, so even constant was non-trivial for them, that the people had some stock fox, I think some sort of maybe pairs, all working on this, improving this K-MST. It's a very important problem that you want to connect this. We will talk more about this problem. But anyhow, for both this problem, there is a constant factor approximation. And so then you can consider these are the K version. These are the incremental version. I'm just giving some of the examples. So the other one was, for example, K-set cover. And what is the K-set cover? Is that you want to ask for a minimum cost collection that covers at least K elements. So I will put an ordering of the sets. So these are the ordering of the set. So if you want to essentially, here in the K-set cover, essentially, you want to ask for the minimum cost of collection that covers that. So it is more like the K coverage problem, essentially here. Yeah. So there is so this is, so hopefully there's some noise. It is not an earthquake. I was actually in this building the previous time that an earthquake came. But yeah, okay. So this is the thing for the K-set cover is more like, in some sense, K coverage problem. So here, what is the thing? I want to give essentially an ordering of the sets. So whenever you want to cover K elements, then just take the first few sets until you cover the K elements. So I'm giving essentially this, I will say, probably they call it K cover, I think, but you can call it K coverage in some sense. It is a bit, I mean, K set cover is a generalization of K coverage in some sense. That anyhow, this is the things I'm giving an ordering of the sets. Whenever you want to select K elements, just go through these sets and choose them as soon as you will have K elements and stop. So this is the thing essentially is, this is the work that was done by this set of Rajarman and a few quarters. This is this paper. You can just search this one about. Yeah, I think that was 2 papers that got merged essentially. This is also David Williamson was part of this as well. So this is anyhow from 2006. They show that there is actually, for any of these problems, there is order 1 incremental solutions for K-median, K-MST, and then log n for K-set cover. So they show that, so K-MST or this K-median, both of them have constant factor approximation. These are non-trivial. But they show that there are incremental solutions which are also order 1 approximations. So that's a very good thing, essentially. So you don't need to pay anything extra. For TSP was constant to universal, you need to pay log. But here you don't need to pay log. For this kind of incremental solution, actually there is an order 1 approximation. So you may pay a little bit more extra. There is some alpha times. So alpha, if the alpha is the best approximation for the approximation, then they can turn alpha something for the incremental version. But they can, this one, they can get it for K-median, K-MST, and log n for K-set cover. As I mentioned, like generalization of K coverage. Good. So as I mentioned, so the people also have, I mean, consider instead of K-Steiner tree, also they have considered instead of K-MST, K-Steiner tree. That would be a bit different. And then you only care about the terminals. So it is, in that case, it would be more, you don't care about all vertices, only about these terminals. And for that also, they got some universal solutions. So when you don't care about all vertices, you want to get some solution, incremental solution for the terminals that are given. Also, there are the case that, I mean, there are some work that has been done for this kind of things that here we talk about, for example, some of this about log n. The question that some of this can be get polylog k. So if you want the solution for k demands, the approximation should be polylog k. That would be better. So if like essentially if your solution is just asking for demand 5, then it should be somehow proportional to k and hopefully log k, not log n, because log n would be much larger. So this is especially this paper of Anker Moitra that he has considered for cut problems. Anyhow, so these are a few set of problems that this kind of universal. So we had 3 things essentially the same meaning. Universal, then we had oblivious, and last but not least, it's called incremental. And as I mentioned, all of these works in some sense are coming. This universal were there before, but it became again a topic because of oblivious routing that I want to talk more about it. Good. So this thing that we have discussed, they are coming all from this one, and this is the whole concept of oblivious routing that we want to talk more. So let's see what is oblivious routing. And as I mentioned, oblivious routing has 2 things. One was the motivation, essentially introducing all these set of problems, universal type of solutions. The other one is essentially for cut problems, then you can embed it into tree metrics. So I needed to give that such that I can essentially connect this one well with the rest of the lectures. And that's the way that we are going. Now, what is oblivious routing? And we need to talk about oblivious routing before actually going to the cut problems and take the universal solutions there. So this oblivious routing in some sense is similar to oblivious network design. There are some slight definition changes that I will mention. So you are given a graph G, and each edge UV has some capacity CUV. This is a typical, essentially network problem, network flow problem. You are given this source target pairs SITI and a demand DI for each pair. Good. So a demand DI for each pair. You want to find a fixed routing rule to route 1 unit of flow between all possible source destination pairs. Again, how many things we have it? N choose 2 we have. And you want to keep congestion close to the optimum congestion for any set of source destination pairs. So what is the idea? So this is actually something very practical, because there are several network routing algorithms. Like these are, like when you send an email from here to there, essentially, the whole idea is that this email will be chunked into smaller pieces, and each of them are essentially going through different paths. There is several things like it is OSPF, I think, and others that they are trying to find the shortest path. But there are some of these which are the rule-based, and you can actually mention from which path you should send it. And there are like lots of essentially studies of this, and the people are using different methods have been used essentially. And this, like for example, TCP/IP is another thing for this kind of network routing. So these have been, I mean, the center of attention for several years, maybe a bit less now because we are talking more about AI stuff, but still they are very important because this kind of network design still are super important. Why? Because they are now creating networks of GPUs, huge data centers of GPUs, and lots of this still you need to use this kind of basic network theory essentially for routing, etc. Between these ones. But anyhow, this comes and there is such a practical way of essentially that these rules that we have it, they can be used for practical purposes. You remember what was that? The idea is that for TSP, you want to give a universal solutions, such that if a postman wants to go there to these points, it can just, I mean, if there are the demands here and here and here, you will just from here, shortcut, and you will find. This was for universal TSP. But you may say, okay, maybe nowadays this postman actually has a computer, everything has the app, etc. They can compute the best route for him in anything. Why do we need this one? Theoretically interesting, but maybe practically is not the most, practical way. But of course, you can say that these people, generally, they may not have the app all the time, or maybe disconnected or something like this. And it would be good if something happens, you have some ordering printed for you and say, okay, first go to this, then go this, then go this, and then your path would be reasonable. However, this was about the people and like a postman. But one thing that actually works much more important about this routing for, this is the routing for packets or a small packet. So when you are sending an email from here to there, actually it goes through some routers. And these routers, generally, they have a very limited capacity for computations or anything. And there are billions of packets that are going all over the system. So actually, this kind of oblivious routing that you will say which path they should take it is a very important thing, because you have much less resources. You cannot, for each packet, you cannot compute the best route, essentially, given all packets. This would be a very nice thing, actually, if we can give this, and that is the reason that actually this type of routing has been used, that you are giving the whole path to the package, and so that you just go through this packet, through this path, essentially. So this is really practical, essentially, and important. So that's the thing that is, I want to just justify why we consider this. So what is the idea? Here it says that I have essentially one unit of flow. So here, this is the routing problem. In the routing problem, in the oblivious network design, as I mentioned, because of this subadditivity, you could say that always we can send it through one path. Here, it is not the case. You may send, this is a flow that we are sending, essentially, and you may send it through different paths. So this is the one unit of flow that I want to send from here. And say, I don't know, 0.5 is going here, 0.25 is coming here, 0.25 is coming here. And then I send one unit of flow. Now, if you want to send d unit of flow, just multiply everything by d times that. I will send d. So, what are the oblivious routing? Oblivious routing for any pairs of the demands, n choose 2 pairs, I'm giving this path, essentially, between them. So I will say, if I want to send one unit of flow, how you should send? All of them are decided in advance. Good. Now, I want to decide essentially about these routing rules such that for any demand matrix that I have it, like demand matrix, it means that whatever pair that they should connect to each other, send the demand, and whatever demand DI that they have it, I just multiply this by it. This I wanted to get essentially bounded. I want to get it for, this is the thing, you want to minimize maximum over all demand matrices, congestion of oblivious algorithm versus congestion of the optimum algorithm. So you try to essentially minimize, you want to create such kind of rules such that for any demand matrix, you have essentially a bound or guarantee on the cost of oblivious solution, the one that is just using these fixed rules, versus the solution that essentially optimum for this. Good. Now, so these are, I have mentioned the demand matrix I have mentioned. Then I need to also define what is the congestion. Congestion of an edge is equal to the flow that goes through that edge over the capacity of that edge. So for each edge, you can define the congestion of an edge, how much flow is going through this edge over the capacity of that edge. And this capacity, as I mentioned, each edge in our graph, essentially in each edge in the network has a capacity C. So what about the flow? The flow is actually the one that we are sending through this. So depending on which demands you are coming, then each edge may get some flow from different pairs. Maybe some from here, another one from here. So this edge essentially gets flow from three different demands, essentially. The total flow of that over the capacity of that edge, that is called the congestion of that edge. And here, of course, here you want to do, so what do we do? So if, this is the first thing, if the capacity is, if the flow are given to you, if the demands are given to you, you can write an LP such that minimize the congestion for that. Like essentially you want to consider the congestion of an edge and you try to minimize congestion. So that is the objective function. You try to minimize the congestion that you have for all edges. You can write an LP to do that. What do I want to give it? I want to give you these rules in advance, such that whenever you are just using my rules, this is my routes, I can compute the congestion of the edges under my route because this is how much flow for each edge is going and divided by capacity. The congestion that I will get it through this oblivious routing and the congestion that I will get it optimally through LP, they should be comparable. And this is the first result that Harold Räcke mentioned, and mentioned that as actually polylog is possible. And currently, actually, this has been improved. I think the early one was log n to the 4. The current thing, actually, you can get it almost log n or O tilde log n. And this, through two things, this is through two approaches of, like, it is called decomposition trees, that later, essentially, so there is a decomposition tree that later it turned to become actually a probabilistic embedding into trees. And it shows that actually these are the, so essentially when Harold presents this result, Harold Räcke presented this result, I mean, was so non-trivial that, like, he was telling me that actually some people well known in the field, they were reading this paper and said that when they just see the title, oh, this paper should be wrong. There is some bugging. There is no such bond. Cannot be such a bond. But it was true, and he could get log n to the 4. Then he got the best paper award actually here in this Fox. And then a few years ago, later, he said that if you want, you can actually improve it. It is not completely subsume these results as we discussed, because here the first result he's giving one tree, in the next one you are giving several trees. But so that actually you could use Bartle embedding, a dual of Bartle embedding, to give essentially better bound like log n. He got, because it simplified the previous one, it was very complicated, he got another best paper award. It's like, I think it's like 2008, if I remember correctly. So Fox 2004, and then it's like 2000, if I remember correctly. So that's the thing, and we want to talk about these ones because these are, again, some beautiful things that have been done, and this is somehow in the theory or foundations of network design, these are very super important problems. So this is the things. Again, in the oblivious routing, I want to give the demand between any pairs. We will send my rules for the flow, but any demands are given to you, you can actually optimize your things for that. And you want to have it some kind of comparable, and as I mentioned, comparable polylog first, and then it was O tilde log n. Actually, I think you can get log n as well using just FRT version of that. Okay, so let me clear this and then we will go through this. So let me give you some results here, and then we can go from there. For undirected graph, as I mentioned, this is as I mentioned, we talk about competitive ratio, and we will consider the worst case. The first result, actually, I think it was log n to 3, and it was by Räcke in Fox 2000, not 2004. So the first result was log n to the 3 by Harold Räcke in Fox 2002. Then it was improved by, some quarters and Räcke log n to the 2 log n. It was SPA 2003, and there was order log n by Räcke in STOC 2008. And these two papers got best paper award. The first one because it was very non-trivial. The second one because it simplified a lot the previous and connected with the previous things. However, for a directed case, if you consider, so everything here for undirected graphs. For directed graphs, there is a lower bound of square root of, and it was this stock paper and or soda paper. We both consider this one, even for single source that I will talk about. Now, there is, as I mentioned, for directed graph, there is no hope. And this one, even for the single thing case. What's the meaning of single things? The single things means that essentially, even if you consider, if you are this guarantee is given to you that all these demands are going to one particular vertex. So all of them essentially in the form of Si to T. All your demands. So you can restrict the demands. Say, okay, maybe you cannot get it for all demands, but maybe I can get it for some demands that they have some special forms. And what are these special forms? I mean, it can be something like a Si to T. And like all of them have the single force. Can we get at least for this one some positive results? And as I mentioned, so this was for general case. This one essentially we say that for even for single things directed graph we cannot get. However, this was another restriction that we could get it. What about if we know that these demands are coming from some probability distributions? So then the network, okay. So the issue is that, how can we get something better for directed? Because directed we cannot get it. That was the idea that we had it essentially. So that was the thing. So that, okay, maybe these demands, we can say that these demands are coming from some, these demands between any pairs are coming from some distribution, and these are independent. That is very important. If they are dependent, then it doesn't work. Then actually for directed graph, we could get log n to the 2, and we could show that you cannot get better than log n. This was a stock paper that I had it with Tom Layton, I think Hajiaghayi, Layton, Räcke, and I forgot, I think it was another quarter that we had it. That was in stock, I think it was stock 2005 or 2004, yeah. It was a stock paper, 2000 something. And we show that you can get log n to the 2, but there's a lower bound of log n. So it was quite non-trivial, actually, if you have this assumption. But again, this is very important. These demands that are coming between these guys should be independent. And it is not a bad case, because in the internet, this is like so many parties that you can maybe think about it, or one party cannot control it. However, this for undirected does not help that much. In the undirected, you could actually show that, you can get log n as before, because even if it was worst case, the previous case was worst case. Whatever adversary wants, whatever the demand, whatever pair that it wants, still you could get log n. So with random, we cannot gain anything. And actually, we can show that there's a lower bound. You cannot get anything better than log n over log n. I think this was the soda paper that we had. This was Bobby Kleinberg and Tom Layton and Harold Räcke. So this was essentially the state of the art for this problem. So if you consider this undirected graph, we can get polylog. And this is like adversary is very strong. It can choose. So here we talk, in some sense, when we talk about oblivious solutions, we always talk about adversary. Of course, in approximation algorithms, also there is this concept of adversary that we are talking about. But we have more of adversary in this kind of universal solutions. In this kind of universal solutions, I mean, we are just playing with the adversary. Adversary choose which demands it was have it. Here, adversary decides which pairs it should be there and what would be the demand between them. That's the role of adversary. And we want to essentially be competitive with such adversary. For directed graphs, even for single sink, if we say that all of this demand should go to one vertex, it cannot get better than a square root of n. But this but the issue is this one. But what is the issue? The issue is this, that I mean, for directed graph we cannot get it. If we are assuming the random demands, then we can get log n to the 2. For directed graph, there's a lower bound of log n. For essentially for undirected graph, this random assignment, this random thing coming from random distribution cannot help that much. Still, we can get upper bound of log n as before, and then the improvement would be, I mean, there's a lower bound of log n over log n. I think we don't have the tight result yet. And these are the results that I have it essentially, both of them. Good. So that's about this one. Let me just mention this algorithm essentially. This I wanted to say, this is an interesting example. This is a very good thing. So here, I want to say that this is the claim that I want to say. I mentioned that for single sink case, so everyone wants to go to the single sinks, to this thing. I want to say that in this case, you cannot get anything better than a square root of it. Say why, essentially. Consider this graph. So what is this graph? So this is the graph, essentially. A vertex T is there. This is the sink. These are K vertices here. And then for any K choose 2 vertices here, there is one Aij. So BIs are B1 to BK. And what about Aijs? Essentially, for any K2 pairs, we have Aij. And we are assuming that, I mean, we have only, I mean, I should be less than J or something. What is the size of this graph? The size of this graph would be 1 plus K plus K choose 2, which is essentially order Ks. Good. Now, each of these Aijs only connected to Bi and to Bj. These are the pairs that is connected. And say this is the directed graph that we have it. Everyone is going to the root. All the demands you may think of, all these capacities are 1 as well. Because we need to talk about capacities because we want to talk about congestion. Congestion is that how much flow over the demand that we have. Now, I want to say that in this graph, there is no oblivious algorithm that is better than square root of n competitive, which here in this case, square root of n would be essentially order K. Okay, so how can we show that? Good. So what was the definition? He said that, okay, this is for 1 unit of flow. Each of these Aijs need to say, how should I send 1 unit of flow? Good. So maybe this one say that, I don't know, 0.7 goes here, 0.3 is going here. For all of them, I need to say that. So each of them is just deciding about the flow, how should it go. So how many pairs do we have here? I have K choose 2 pairs, correct? How much flow they should send it? They should say essentially order K times K minus 1 over 2. This is the total flow that they need to send it. Independent of how do they route it, which way, I mean, how much is this one, how much is this one? This is the K over this. So this total flow should go from this all these AIs through this. So this is the A, this is B, and this is T. So this K over 2, essentially K to the 2 flow, that should go from A to B. Here, how many B we have? We have only K. By simple averaging, it means that at least one of these things has, I mean, K times K minus 1 over, so we have this one, K times K minus 1 over 2 divided by K. So at least one of these BJs, say, it should have K minus 1 over 2 demands that are going to this. K minus 1 over 2 flow, essentially. Yeah.
So the term of one of the things is going to be T. The sources are going to be Aij.
Yeah, the sources would be Aij. I mean, the Bijs, I mean, we can say that. I mean, this is actually, you can consider Bij also has a demand, but I mean, adversely decide which demand should be there. I say, okay, Bijs are 0. I don't care about it. I only want to put the things there.
How much demand do you think you're going to put? Like,
I mean, always in the oblivious routing, you will send the demand 1. And if this is the, so if, what about how to scale it? Then you will type it D times that. That is some kind of rule. What is the rule? You will just say for 1 unit of flow, how do you route it? If you have D unit, then on each of these paths, you will say D times that.
It's the algorithm then, so like what is the adversary's input, like what the demand?
I mean, say, I want to say that essentially, anyway, like adversary, here adversary also put the demands 1. So these are exactly the adversary that is putting 1. So for the demand 1, as I mentioned, so you need to decide in your algorithm, in the Oblivious algorithm, how do you send it? Whatever you will send it, you will send a total K over 2, K to the 2 here. It means that one of these Bijs has a order K, or more precisely, K minus 1 over 2 flow that goes from Bi to T. Good? Now, so this flow essentially is coming. So you know that K minus 1 over 2 is coming there, correct? But who are these people who are coming from the BIs? Essentially, these BIs, all the flow that is coming from here, it comes from some AI J, where J is not equal to I, correct? Because these are the, who are the people who are connected to BIs? All the pairs that they have I, essentially. All Ij, essentially, that one is I, the other one can be J. Good. Now, let's see this one. Now the adversary can just send the flow of 1 here. So what is the, now the adversary is doing that. So this one essentially is the thing that adversary sees your unit. So your oblivious routing, say, okay, you are doing that. So one of these BIs, you need to send K minus 1 of 2. Now, this is the demand that I'm giving. For all these AIJs, I'm giving a unit demand to you. What would be your congestion? Your congestion, because anyhow, K minus 1 over 2 of this is going there. So you have, and the capacity of this edge was 1. So the congestion of this edge would be order K. What the adversary can do in an optimum. So adversary and optimum play with each other. Each of these guys have a separate private path through the other pair. Because each of them is Ij with some J. Each of them have a private path, essentially. They sent this 1 unit of flow through that private path. What is the congestion of adversary or optimum in this case? Would be 1. So in this case, we have the opt or adversary. They have essentially 1. Oblivious algorithm has order K, and what was K? It was square root of N, essentially. So it says that if we have a directed graph, then we cannot get anything better than square root of n. That's the best that we can. And actually, in this paper with Harold Räcke and Tom Layton, we showed that this you can actually for single source. So for single source, directed, you can actually get order square root of n, O tilde square root of n. So this is tight essentially. You can get O tilde square root of n, and you cannot get anything better than that. As I mentioned, unless you are doing the randomness. One other thing, it is important. So this is the random. If you add the randomness essentially for undirected, then you can get it up to log n to the 2. That was a structure for directed. Okay. The randomness is that, I mean, these demands are not completely synced. They are coming, each of them, there is some distribution that you know that in advance.
Oh, you mean that random? Okay.
That's randomness, yeah.
Okay. But I was wondering one other thing. So right now, what's happening is you have, so like when you pick your solution, it's gonna be like you're gonna have to put a lot of weight on one.
Yes.
And like the adversary is gonna
yeah.
keep going. So what if you don't what if you pick your solution randomly?
I mean, this is the definition of oblivious routing, that you are deciding which one is going there. So you need to somehow, in some sense, the randomization is already there. The fact that you will spend half of the time, this is another thing. You can think about oblivious routing as some kind of randomization. What's the meaning of that? When there is a pair essentially between these two people and one half, so it is, I don't know, 0.5 here, 0.2 here, 0.3 here. It means that any packet that you will get it, with probability half you will send this, with probability 0.2 you will send through this path, and with the other probability 0.3 you will send it this one. So in some sense, oblivious routing has already randomness in it.
Yeah, but
you might define some other versions of that, but I'm sure that that does not help, because essentially this already captures the randomness, and it seems that that would be, again, any of such kind of positive result is amazing. That's the whole idea. Why this paper was in a stock? Because we show that if you get it random, these demands are coming from some random distribution that are given, then you can actually get polylog. Anything that you can get polylog is an amazing result, and the people will appreciate it. And generally it's non-trivial. By default, there is no such results. And that was the thing that I mentioned for Harold Räcke result was quite, the people expert in the field say, oh, this should be wrong. There is no such thing, because it's very unexpected. Let me add just one final note here. So we talk about three versions of the graph. So we talk about edge-weighted. We talk about node-weighted. Both of them undirected. And finally, we have the directed graph. In the directed graph, edge-weighted and node-weighted are generally the same, because there's some reduction between edge-weighted and node-weighted that makes them the same. So edge-weighted and node-weighted are essentially the same for directed graph. But for undirected graph, edge-weighted and node-weighted are different. And generally, node-weighted, as I mentioned, it can simulate edge-weighted, and it generally is harder for some. So here you could actually show that if you consider the node-weighted graphs, so in the node-weighted graphs, so here we have the capacities on the edges. What about if we have the capacities on the vertices? You can define this one actually. If you define this way, still this example actually shows that for node-weighted also the bound is square root of. And what is the idea? Why this is the idea somehow is this one. When you consider this is the idea for node weighted, generally yeah. So the one question is that why this example that we have mentioned, if it was undirected graph, it was not so say we remove all these directions. Why it was not a bad case for directed for undirected graph? The main reason then in that case, then these guys are going there, then BI does not directly send the flow here. BI randomize the flow to different things, and then it sends it through different pass through this. So BI does not send directly to T, it sends it back again to some of these AIJs, and these AIJs essentially route it in a different way. That's the thing that calls the. However, if you consider the node-weighted case, this cannot happen because as soon as they will hit the BI, the congestion has happened. How you don't send it to T, but the congestion happened on the node itself. So in that case, the node, after when these guys are coming to BI, already the congestion happened. So in the directed case, the congestion happened on the edge later. But here, when it is a node weighted, the congestion already happened here. So then sending back to AIs does not solve the problem. And this is essentially the square root of n lower bound for the same example, square root of n. So for node weighted, undirected, or directed, edge weighted, or node weighted, these are the same. You cannot get better than the square root of n, and you can actually get for the single thing, you can get a square root of n. But for undirected, edge weighted, you can get. We will talk more about it, about this, how can we get it, and this, so far we talk about these two applications for routing and for this kind of universal solutions, but we didn't talk, that much about this kind of embedding into tree for cut problems, and we will talk more in the next session. If there is nothing, then no question, we will stop here.